Good afternoon, everyone. Welcome to Network Seminar Series hosted by the Center for Network Intelligence at the EC and RBC CPS. It is my pleasure to introduce today's speaker, Sandeep Rao, and he will be speaking on signal processing challenges in mmWave radar. Sandeep Rao is with Texas Instruments, where he leads the R&D group on mmWave signal processing. His research group works on identifying new applications for mmWave sensing and is actively involved in defining the next generation of TI mmWave radar devices. Earlier, he led the GPS positioning algorithm development effort at TI. Prior to TI, he was at Hughes Network Systems, where he was involved in the development of modem algorithms for satellite communications. He has a master's from the University of Maryland and a bachelor's from the Indian Institute of Technology, Madras. So for the audience, you are encouraged to ask questions at any point during the talk. And for those attending online, please, you can unmute yourselves and ask whenever you have any questions, or you can put your questions in the chat box and we'll relay it to the speaker. Over to you.
It's fine now? Okay, cool. So let me just start by telling you what my goals are for this talk, right? So millimeter wave radars, in the past few years, there's been a lot of activity around this. So several companies, Texas Instruments included, are bringing out newer millimeter wave radar chips, every year. There's also a very healthy startup ecosystem around these radars. And from the academia side also, there's a lot of research going on. So if you look at any of the flagship IEEE conferences, right, there are special sessions dedicated to millimeter wave radar. Like last year's ICASP, there were 2 sessions on automotive radar. In the European Signal Processing Conference, there was a special session on mmWave radar and AI. And of course, there are then specialized conferences, IEEE conferences for radar, like IEEE radar conferences, URAD, and so on. And recently, there was also, I think maybe 3 or 4 years back, IEEE transactions on radars was also started. So the first part of my talk, I want to kind of give you guys a sense of, what are the applications of millimeter wave radar, and a sneak peek into how this technology works, right? So the second part, so a lot of the advances in millimeter wave radar, right, are happening also because of research that's happening in the in academia. So in the second part, I want to highlight some important or useful and interesting research areas in this that are useful for industry, right? So if you are looking for research problems and want to work on something that's relevant to industry, I think that will be a good start. And my background is signal processing, so the topics that I'm going to be covering here are kind of going to have a signal processing view to it or perspective. Okay, so let's start. So yeah, this is the kind of outline of my talk. Okay, so question, when was the first radar invented? Any guesses?
1894, something like that.
Okay, I think that is right. I just looked it up in Wikipedia. I think that also was mentioned, but I think radar was really used a lot, and kind of a lot of innovation was there around the time of 1930s, First World War. It was, or Second World War. It was used. So radar has been in use at least since the days of World War II, if not earlier, right? So, but why are we looking at radar now, right? Okay, so the thing is that technological advances have resulted in these devices becoming smaller in size, lower in cost, higher in performance, and TI built one of the industry's first radar on a chip solution. So it's a chip which has the starting from the RF baseband, signal processing, everything, it is done on the single chip, and this chip is around 12 mm by 12 mm. Of course, there are other companies also which do similar things. So for this kind of a device, AWR2944, which has been in the market for, I think, maybe a year, right, you have to have antennas on the board and connect them to this device, and everything else is done by the device. The position, location of the targets, maybe even tracking them, classifying them, all of that can be done on this device. There is also a class of devices which we call as antenna on package or antenna in package. Some companies call it antenna in package. We call it antenna on package, where the antennas are also on the package. And those are usually used for more closer range applications. This kind of a device is typically used in automotive radar, where you have to see up to, let's say, 250 meters plus. So to build such a chip, it's a multidisciplinary team. So you have people who are experts in RF analog, IF analog, digital design, signal processing algorithms, and so on. And these devices typically operate in either 60 or 77 gigahertz bands. So 77 gigahertz is for automotive. So 76 to 81 is the band. And the 60 gigahertz band is for non-automotive applications, such as maybe building security or consumer applications and so on. Okay. So radar applications, when you think about it, right, radar is obstacle detection, right? That's how everybody recognizes it. So the biggest market for these millimeter wave radars is automotive. So a lot of the cars, you see on the road, especially in the US, Europe, China, and so on, right? Japan, you have these radars built in, which are mainly used for driver assistance. So if you're blind spot assist, cross traffic alert, and so on, right? And some of the cars in India also have this now. So that's the bulk of the market for automotive radar. You're also seeing them, because of the reduction in cost, in things like drones. A lot of drones nowadays have radars, robotics, maybe traffic monitoring. But all of this is basically around the theme of obstacle detection, right? The other thing about radar, and we'll get a little bit of this later on, is that radar can sense very fine motion. So it's very sensitive to fine motion. So because of this, right, and because of the fact that these radars are getting cheaper, there's a lot of emerging applications such as gesture recognition, vital sign monitoring, live presence detection in a car, intruder detection, and so on. There are other applications, building automation. So building automation is basically building security. So intruder detection in a building. Also for smart buildings, how many people are there in a room, or is there somebody in the room, and so on, right? Level sensing. So radar is also very good at precise range measurement. So in industrial applications, there's a need to measure how much of fluid there is in a particular tank and so on. So industrial level sensing is another application. So some of these applications use 77 gigahertz, some of these use 60 gigahertz, primarily driven by the regulations, primarily driven by regulations, right? Okay, so this is a chart, this is a table here. Maybe I think if some of you can guess or give me a sense of which of these, so I wanted to put here in perspective, right? How does radar is a sensing modality. How does radar compare with other sensing modalities? So other sensing modalities in a context of a car, for example, the most obvious one is camera. Of course, you have LiDAR as well. So if you look at camera and if you look at all these properties of sensing, right? Maybe you guys, can you tell me radar range and velocity estimation, which is better, radar or camera? Okay. By the way, the answer is not radar for everything. Spatial resolution, which one is better? Camera. Reading signage and lane markings, camera. Night vision, adverse weather condition, and aesthetics. So aesthetics is primarily around, so the aesthetics here I mean by, you can put radar, you can make radar invisible, because radar is, plastic is transparent to radar. So if you put it behind the bumper, for example, you will not know that you placed a radar behind it. So you don't have to make a hole or put a lens or things like that, right? So, okay. So this is the, how these two compare, and you can see that camera is very good in certain things, radar is good in others. So, that's why radar is a very good complement to camera. By the way, if you look at LiDAR, right, one of the main, LiDAR actually has good range resolution as well, good spatial resolution. I'm not sure about reading signage, but it can do night vision as well because it is generating its own signal. The problem with LiDAR is one of it is cost, definitely, right? LiDARs are extremely costly. Even though they are trying to bring the cost down, right, it's still orders of magnitude compared to a radar. For example, some of these radars that we build, you can get them for $10. That is the kind of cost. Other disadvantages with LiDAR is adverse weather condition. So radar operates at millimeter wave while LiDAR operates very close to visible light. So because of that, the physics of these different wavelengths, LiDAR will be attenuated more in fog. And interference from sunlight. LiDAR also has interference from sunlight. Okay, so the next part, give you a quick introduction to FMCW radar. So FMCW radar actually stands for Frequency Modulated Continuous Wave. And this is the modulation technique that is used by pretty much all radars that are right now on the road. I think when you talk about millimeter wave radar, we're almost always talking about frequency modulated continuous waves. So I want to give you a brief introduction of how this kind of radar works. Okay. I think I had some of the slides here. Maybe I might mistake something. Okay, that's fine. This FMCW radar, right? The basis of FMCW radar is a signal called a chirp. And a chirp is basically a sinusoid, a sine wave, whose frequency increases linearly with time. So it has a certain start frequency, and then it's increasing the frequency over a period of time, right? Okay, so this is the same chirp here, a frequency versus time view of this chirp. So this is frequency versus time. So typically, the start frequency could be 77 gigahertz, and the end frequency could be 79 or 81, depending on the bandwidth of the chirp. So how does this radar work, right? Basically, you have a transmit antenna. You have a synthesizer which generates. How do I? Oh. Okay. So you have a synthesizer which generates this chirp, right? It has to be a very linear chirp. It's sent to a transmit antenna. You have a power amplifier. So this is a very simplified view. It hits a target. It comes back. So this here actually is the transmit chirp, illustration of the transmit chirp. So this transmit chirp is reflected from a single target in this case. You can have multiple targets, and the radar can sense all of them simultaneously, but it's, here in this case, it's one target. So you get a reflected wave, and that reflected wave comes with a certain delay. So that is the, reflected wave over there. It's a delayed version of the transmit signal. So then you have a mixer here. So the mixer is mixing the transmit and receive signal. So a simple way to understand the mixer is the output of the mixer is the difference in the frequencies of the two inputs that are sent to it. So in this case, you have two frequencies, two chirps here, and if you look at this common portion where they are overlapping, right, the frequency difference between these two chirps, even though the frequency is changing, the difference is constant. So that difference shows up as a tone here, which is basically a sine wave of fixed frequency. And that frequency depends on how far the second received signal is compared to the first one. What you do typically, right, you take this IF signal, you will have an ADC there which will sample the signal, you do an FFT, and then you can get all the frequency components in this signal. So basically, right, this x-axis is frequency, but it's also proportional to range. So here, for example, there's one target, so there's one peak. If there were multiple targets, there would be multiple peaks here, and the further the target, the larger the frequency. And the weaker the target or the further the target, right, the peak would be smaller, and so on. So basically, it is, it's like a range plot, you can say. Okay. So this FMCW radar, right, so if you typically think of radar, right, the simplest thing is you send a pulse, the pulse comes back, you check what is the difference of the time between the transmit and receive pulse, and you can find out how far the target is, right? But the industry uses FMCW radar. So what is the difference between pulse radar and FMCW radar? So FMCW radar has some nice properties. So one thing is, so some of these properties here, right, I'm kind of just mentioning them here, but we do have some, I can give you some links to some, introductory material which can kind of give you more insight into these. But it turns out that the range resolution of a chirp depends only on the bandwidth spanned. So for example, what is the start end bandwidth minus the start bandwidth? So if you look at a pulse radar, right, a pulse radar, if you want to get okay, an important aspect or a metric for radars, right, how good they are, is something called range resolution, which means if you have two targets very close to each other, right, can you perceive them as two targets, or do they get smudged into one target? So range resolution means, very good range resolution means if you have two targets, you know, even a few centimeters apart, you will be able to sense them as two targets. So in pulse radar, if you want to have very good range resolution, right, you have to have a very narrow pulse. So if you want to have a radar which can have a resolution of a few centimeters, right, these pulses have to be extremely small, you know, fraction of a nanosecond kind of thing. And to sense when this pulse has arrived, right, you have to have very high sampling rates for your ADCs. So giga samples or more, multiple giga samples actually, right. But if you look at FMCW radar, right, it turns out the range resolution depends only on the bandwidth of the chirp. So it doesn't depend on how narrow the time period is. The ADC sampling is largely independent of range resolution. So typical FMCW radars today have resolutions of a few centimeters, but the sampling rate of the ADC is only tens of megahertz, you know, not tens of gigahertz. The other thing is, if you want to see very far, right, you have to put a lot of energy into the radar, into the transmit signal, so that it can go very far, hit that far away target and come back. So if you talk about pulse radar, right, first of all, we want it to be very narrow because we want good range resolution. Now, if you want this pulse to be also having a lot of power or energy in it, right, you have to have a very strong pulse which is very narrow, which is not very easy in, you know, from a analog perspective. On the other hand, FMCW radars, the energies can be spread because it is not dependent on the, pulse width is not related to range resolution, right? The energy can be spread across a larger time duration. Also, you know, we said it's a sine wave, even though the frequency is changing, so it's a constant envelope signal. So again, that is, you know, makes for efficient power amplifiers. So these are all the nice properties of a chirp, which is why, you know, people are using this overwhelmingly in the industry. So far we talked about range resolution, right, or range estimation. You send a chirp, you get it back, you mix it, and, you know, you do this FFT, and you can find out how far different targets are. Now, yeah. Yes. So one thing here, right, when you talk full duplet, I think, okay, you will always have some antenna coupling, which basically will show up as a very close by target, right? And typically before giving this to the ADC, so the LNA will definitely see that close-in reflection. But after the LNA, right, the thing is that all these close-in reflections come in at very low frequency. So you can put a high-pass filter and remove that. So before the ADC will not see that coupling. Yeah. Yes.
You have information from the frequency that tells you the range.
Yes.
But perhaps the amplitude also, how do you combine the two?
So the amplitude tells you the radar cross section. So amplitude along with the range tells you the radar cross section. So if the amplitude is higher, it means a lot of reflected signal has come back. If the amplitude is lower, it means lesser reflected signal has come back. Now the reflected signal being more or less, one thing, it depends on the range, because the further it is, it's an R square and R square, so it becomes R par 4. So there is a natural tendency for targets which are far off to be weaker, so the amplitude to be lower. Additionally, it depends on how much energy that particular target is reflecting. So once you see a peak here, right, you will know the range. So once you know the range, you will know how much attenuation has to happen, you know, based on R par 4 and based on your noise figure and transmit power and so on. So
frequency a better signal, or
frequency tells you the range.
Yeah, that's what. So
yes.
Is that a better signal of the distance or the?
Yes. No. Frequency is how range is measured. The amplitude only tells you how weak or strong the target is, right? So that you could use, for example, to maybe one of the features that you can use for classifying is that a big target or a small target or so on, right? Okay, so radars, right? I think they actually can estimate range, velocity, and angle, all three. So far we've talked about range. Now let's talk about velocity, right? So we talked about you send one chirp here, right? You have a single transmit antenna, you have a single receive antenna, you send a chirp, and you can estimate the range of targets. Now to estimate the velocity of all these targets, right, it turns out you have to send multiple chirps which are equally spaced. And what happens is that we look at phase changes across the sequence of chirps to measure the velocity of targets relative to the radar. So this is all measuring targets velocity related to the radar. So, one chirp is for measuring range, A sequence of chirps, we typically call this a frame in radar parlance. So a sequence of chirps is used to measure the velocity. In addition to the range, it's used to measure the velocity of targets. So if you look at the kind of computations involved, right, you have a single chirp. If you send, you will get a bunch of ADC samples on which, I showed you we take an FFT. And you will get some peaks, so this is just, showing some peaks here, illustrating some peaks. So these red things are strong targets. And they tell you what the range of these targets are. Now, if you have multiple chirps, right, each of these chirps will give you some samples on the output of the ADC. You can place them like this, as a square or a rectangle. Actually, it's a rectangle. The length and breadth doesn't have to be equal. But you do then a two-dimensional FFT on this, and it turns out, right, that what you get at the output will be like a two-dimensional plot where the x-axis is range and the y-axis is velocity. So if you see a target here, a strong target here, this matrix value has a high value, right, this cell here. You look at its x-coordinate, you look at its y-coordinate, you can find out what the range and velocity of the target is. So that's how you do velocity estimation. So we've done range, we've done velocity. Third one is, so now we also want to measure angle. So far we've been talking about, one TX and one RX. So one TX and one RX, but multiple chirps. So that's enough for range and velocity. The moment you want multiple, moment you want to estimate the angle of a target, you need to have multiple receivers. So it's a single transmitter here is transmitting the sequence of chirps. This one? So samples is, okay. Okay, so here, actually, this is an IF signal. You put an ADC here. Okay, so the output of the ADC is what I'm referring to as samples.
You send a single chirp and this one is a sample of that.
Yes,
Okay.
yes.
And the second one, you send multiple chirps, but each one of them you
Correct. So each of one of them, since they're separated in time, each one of them will give you a similar vector of samples. Yeah. So this is, for example, samples from the first chirp, second chirp, third chirp, and so on. And you do this two-dimensional FFT.
When you say single chirp means like you actually sending signal in time actually from, let's say, 0 to T or whatever, right?
Yes.
And so you are actually sending multiple chirps simultaneously, right?
No, not simultaneously. It's one after the other. So this is, for example, right, this is time.
So you, okay.
It's
so
after one you send the
finish,
next
you
one.
finish sending one chirp, then you're
Correct.
going to start second. Okay.
Correct. Yeah. Sure.
So we need a phase coherent system for slow time
Yes.
velocity
Yes.
extraction. Now, what happens is that when you go from one chirp to the next,
Yes.
typically this is generated by a PLL, right?
Yes.
And the PLL probably comes to a state where the initial phase is not the same
Correct.
for the two chirps.
Correct.
Is this a signal processing problem that you fix, or does the hardware have to take care of it?
No, actually the hardware automatically takes care of it. I think good question. So here you have this mixer, right? So what happens is if there's an arbitrary initial phase, that phase will get cancelled in the mixer. So, your PLL stops and starts again. And when it starts again, it can have arbitrary phase, right? Some phi naught phase, but that same phi naught phase is carried on the receiver as well. So those two cancel off and it doesn't matter.
Unless the target is moving, in that case.
In case the target is moving also, right? The target is moving.
But that's
I mean,
what
okay,
we're trying to measure.
Yes, correct. So the phase change due to the target's motion will be captured. The phase change that you are putting in will be cancelled out. That your oscillator or synthesizer is putting out, right? That initial phase will be cancelled out. Yes.
Thank you.
Does the ADC clock and the PLL reference needs to be generated by the same crystal oscillator, or they can be generated using different ones? That can
It
introduce
is,
some phase mismatch or something.
Yeah, it is by the same. So we have one crystal which does the whole thing in our system.
Okay,
So it
gives
has
the
to be the
same,
same.
the clock to
Yes.
the ADC also and gives the
Yes.
reference to the PLL.
Yes, yes. And in fact, that question is also important in the context of cascading, when I'll talk about later, but it has to be the same source.
You have a sudden change in phase.
Huh.
Is there some simplification that, or the nonlinearity can be avoided when
Which
you
nonlinearity?
have the phase suddenly changes when you change from one chirp to the next. you don't have to change the phase though.
So usually the PLLs,
Will do a continuous
it kind of
wave.
has to start again from scratch. You also want to save power in between. You don't want to, and you want to anyway ramp down very fast. So you go from, let's say, 77 gigahertz to 81 gigahertz. Actually, not this one. Let's take here, right? So here you have this transmit chirp. So it starts from 77, goes to 81, for example. You have to quickly, as soon as possible, come back to 77. So during that ramp down time, right, it's very difficult to maintain, or we don't try to maintain phase coherence. It comes down as fast as it can, and then it starts off again, and it can have a different phase. But that doesn't matter, actually, because of the way it cancels, it is not an issue at all for us. Yeah, so so to measure the angle, you do need multiple receivers, okay? And just like we said, phase changes across sequences of chirps are used to measure velocity. You measure phase change across multiple antennas to estimate the angle of arrival. So this concept is the same even in any system which uses multiple antennas to estimate the angle of arrival. Of course, here I'm showing one TX and multiple RX, but typically we use MIMO radar, so they will have multiple transmitters and multiple receivers, which mathematically you can, is equivalent to one transmitter and a whole bunch of receivers, but usually it is done as a MIMO radar scheme, which will also have multiple transmit antennas. So carrying over that analogy, where we said 1D FFT for range, 2D FFT for range and velocity, right? Here it was a rectangle. Here you'll get something like a cube where you will have samples and chirps and an additional dimension of antennas. And assuming these antennas are all linearly spaced, you can do a 3D FFT. So FFT along all these dimensions, and you will get this cube or cuboid, and there will be cells here which have strong signal values. You can read the XYZ coordinates of that and figure out the range, velocity, and angle of that of all of these targets. So it doesn't have to be one target; it can be multiple targets. So that's basically this FMCW radar in a nutshell, right? A radar can measure the range, velocity, and angle of arrival of multiple targets in the scene, provided you send this multiple chirps in a frame and you have multiple antennas. So some of the metrics for any radar system, right, is, for example, range resolution. How far, how far do two targets have to be perceived as two separate objects, right? So it turns out that the range resolution is proportional to the bandwidth of the chirp, and it's given by C by 2B, where B is the bandwidth. So basically, larger the bandwidth, you get smaller range resolution, which is better, right? Velocity resolution depends on the total frame time. So you have a larger frame, you have a better velocity resolution, because resolution is inversely proportional to the frame time. The other thing here is actually maximum measurable velocity. So the maximum measurable velocity actually turns out to be, again, inversely proportional to the distance between the time difference between the start of one chirp and the start of the next. So here you actually want it to be bigger. Better Vmax means you can natively measure higher maximum velocities. So you want these chirps to be as close to each other as possible, which is why when you finish one chirp, you really want to ramp down and start the next chirp as soon as you can. The other thing is angle resolution. So angle resolution is proportional to the antenna aperture. So the more antennas you have, you will have better angle resolution. So if you look at resolution, right, larger the bandwidth, or larger the velocity frequency span, better the range resolution. Larger the time span of this frame, better the velocity resolution, and larger the spatial span of your antenna, better the angle resolution. So C, speed of light.
What is the
lambda? Lambda is the wavelength of this radar. So at 77 gigahertz, it will be 4 millimeters.
So I thought what do you mean by that? I thought the chirp band is not what matters, right?
This is the center frequency. So for example, if you take 76 to 81, you can take, for example, lambda, you can use 78.
Okay, in between. Okay.
One more question.
So Sandeep, one question that has, I've always been intrigued by is this: when you're looking at velocity resolution,
yes.
Suppose you slow down your ramp rate, right? In that case, you're getting better advantage from coherent integration. You're integrating for longer, but you have a fewer number of chirps that fit in a frame.
Correct.
But the frame time is the same, so you have the
Yes.
same velocity resolution.
Yes.
So it looks like I'm getting a lot of stuff for free.
No, you're getting the same velocity resolution, but your maximum measurable velocity will be lower, will be worse. Because you will have, the distance TC will increase, because you said slow the ramp, right? When you say slow the ramp, it also means elongate the ramp, right? Because you still want to go from up to B. You still want to span B. So if your ramp is slower, it will take longer to reach B, which means TC, you can start the next chirp later on. So this TC will get larger, basically.
But I get an advantage in SNR, right? Because now
SNR will be the same. So SNR depends on the total exposure time. So the total time that your radar is on from here to here, ignoring any gaps here, right? The total on time and your number of transmit antennas you have is what determines how far you can see, or the total energy you put out. So that will be the same even in your example, where you're saying you're putting out fewer chirps and having them ramp slower, right? So the distance that you see will be the same, but the velocity that you can natively measure, right, will be lower. And the reason is that for measuring velocity, right, we depend on phase change across two consecutive chirps. And if that phase wraps around, you cannot measure it unambiguously. So to prevent that, these chirps have to come as soon as possible if you want to measure larger velocities. I mean, it's like that wheel rotates, you have to have a larger shutter speed, right? Same kind of concept. So yeah, I think what you mentioned, you can see the same distance, but your native measurement of maximum velocity will be compromised.
Thank you.
Another question.
Huh.
So every chirp here is also an improvement on your range measurement because you have multiple chirps.
Yes.
Or do you lose something? Do you have the uncertainty coming from, because it's velocity, range? You have to somehow combine the two.
Okay, so the assumption is that, right, the frame time is so small that during the period of a frame, right, the target's velocity is constant.
Okay.
The target's range is also constant.
Position is also constant.
Yeah, all of that assumptions are made. If not, you will start seeing some smearing.
Okay.
Yeah.
Next question is, if you have a clean slate approach, in the sense
Yes.
that, here the chirp and the sequence of chirps,
Yes.
the multiple antennas seems natural, but the
Yes.
sequence of chirps and the chirp itself
Yes,
seems like a fantastic design.
yes.
If you were to take a clean slate design
Yeah.
and now ask what is the best waveform,
Huh.
would this be, is there some merit to this chirp from a clean slate optimized perspective?
Yeah, okay, I would say, so I have not thought about that question. So one thing I can tell you is that from a simplicity of the analog, right, and simplicity of ADC, frequency modulated continuous wave, which is the chirp, right, the basic concept of a chirp, right, is very easy for designing front ends which are low cost. Higher ADC sampling rate means again higher cost and so on, right? Similarly, your power amplifiers and all that, right? So this chirp concept is a very nice concept. Okay, now once you have a chirp, right, now irrespective of whether it's FMCW radar or not, right, any other radar you look at, the way they measure velocity is they have a basic unit. So in our case, it's this chirp. You can also have a basic unit called a pulse. Now the way to measure velocity is to have that basic unit repeat multiple times. So that seems to be a common theme, which is the same thing that we are doing here. But so, okay, the other thing is that, right, there have been a lot of attempts to dethrone FMCW radar. There are several companies which come up with newer modulation schemes and so on, and that hasn't happened yet, which leads me to believe that this does have some advantages. But I think if we have time, I can just talk a few. I didn't plan to talk about that, but we can talk about some of the other things that people are trying to do, right? What is a goal for the ideal modulation scheme for radar, right?
Regarding the increase in SNR, right?
Huh.
So there is one SNR that is at the interface of the ADC, but after you do FFT, there is a processing gain that you gain in the FFT.
Correct,
So that
correct.
SNR will be increased by the processing gain of the FFT, because if you increase the TC, right, for a given target, like you will get a beat frequency,
Correct.
and for a beat frequency, higher number of cycles will get completed because you have a higher time now. So that FFT processing gain will definitely increase the SNR since your beans are getting smaller and smaller, right?
Processing gain will increase if?
Processing gain will increase if you have a higher TC basically. So that will pull out the signal from the noise, right?
No, okay, so the processing time, the processing gain that you have, right, after doing all your FFTs only depends on the total integration time that you have. It doesn't depend on, for example, if your ADC, if you have more samples for your, see the total, so even if your ADC sampling rate is lower or higher, right? Before you sample, you have to have an aliasing filter, right? That itself has some benefit of noise, right? So if you look at the total benefit of noise from the, starting from the thermal noise that you see, including the gain that you have before the filter, before the ADC, whatever filtering you do, all of that if you do right, the total gain that you can get will only depend on the total coherent gain. So the coherent gain assumes that I'm doing range FFT, Doppler FFT, all the FFTs I'm doing. So all of this samples that I get right across all the samples from each chirp and across all the chirps and across all the antennas, all of that gain is coherent through FFTs, right? But the total gain will be the same. Okay, so I think this is just summarizing what we, so the range resolution depends on the bandwidth, the velocity resolution depends on the length of the time duration, and the angle resolution depends on the, spatial width of that antenna. So in general, right, radars are known to have good range and velocity resolution, but limited angle resolution. And the reason for this is that, right, velocity resolution we saw is very easy. You want to improve the velocity resolution, just send more chirps. So there's no hardware cost to increasing the velocity resolution. Range resolution, right now our, state-of-the-art radars in the industry have, they go up to 4-7 gigahertz. So really limited by the regulations only. So building a chirp synthesizer that spans that large bandwidth is not that difficult, right? But angle resolution, right? Every time you have an antenna, you have to have a RX chain associated with it, which will be RNA, ADC, and all of that stuff, right? So first of all, these antennas will take space. Secondly, all those signal chains that you have to have behind, behind each of these antennas will also cost you area. So in general, radars have good range and velocity resolution, limited angular resolution. So what we've learned so far, I think FMCW modulation enables power and cost efficient devices, de facto standard. By transmitting a sequence of these chirps across multiple antennas, you can measure range, velocity, and angle. So this FMCW radar is, from an analog point of view, it is efficient. From a processing point of view also it's efficient because you just have to do, for basic processing, right, you have to do FFTs, and as long as you have a good FFT engines, it's good. And radars have good range and velocity resolution, but angle resolution or spatial resolution can be limited.
So for the last point,
yes.
Is it possible to combine range resolution and velocity resolution? Is it possible to do the range and the velocity processing using FMCW techniques?
Yes.
And then bring in a beamformer, borrow from the pulse radar world, and do the steering and get much better angular resolution?
So beamforming you can do in FMCW radar as well. I mean, so beamforming is actually...
So I meant more conventional phase shifter based beamforming.
So yes, so we do support, for example, radars typically support also beamforming. So you can have multiple transmit antennas, you can give them a phase shift to focus your antenna on a particular region, right? So that you can do. But irrespective of that, right, whether you do beamforming or whether you do, so there's one thing called MIMO radar where you have to transmit on all your transmit antennas, receive on all your receive antennas. The transmit antennas have to be somehow multiplexed. So you can do time division multiplexing or whatever, right? But then once you get all those signals, for all TX, RX combinations, if you get the receiver, data at the receiver, you can then get a full field of view of what the angle of arrivals of different targets are. In your case, what you're mentioning, beamforming, what will happen is you will focus only on a particular area. So if you want to scan the whole scene, you will then have to, beamform in different areas. But beamforming has an advantage, right? Beamforming has if you know particular location that you're interested in, right? Particular angle, right? You can focus your beam in that direction. You will actually improve SNR. So compared to MIMO radar, where you get a whole field of view snapshot in a single measurement, beamforming can give you better SNR for a particular direction.
You also get the advantage at the TX if you combine the beams, the power goes up, right?
Correct, absolutely. That it will give you an advantage. But in terms of native angle resolution, right, it will still be the same thing. MIMO radar, or maybe this also we can take it offline, something similar to what he asked. I mean, given an antenna configuration, right, the angle resolution is locked. But you can get better SNR if you focus your beam in a particular direction, and you can do that using phase shifters. That is true.
Thank you.
If your transmit antennas are being used only in a time division multiplex fashion,
yes,
then what's the advantage of the multiple antennas? You can simulate the different locations through a different phase on your transmitter itself. Is it just engineering?
Because because see, you have to see physically the antenna has to be. So when an antenna is located in one particular location, if you move the antenna, right, then depending on the angle of arrival of different targets, you will have different phases in the first transmitter and the second transmitter. You cannot simulate a second transmitter placed somewhere else. So suppose you have one transmitter here, let's say there's one more transmitter here.
So target is not known. Yeah.
Correct. Target is not known. So yeah. Okay. So I think there is a YouTube series that you can look at if you want more on to understand more on FMCW radars. Basically, has some of the math in all of this stuff. It's not very difficult. Okay. So I think if there are any more questions on this section, so I think the introduction to FMCW radar I've completed now. Let's see how we are doing on time. Okay. So these are all challenges to you guys. So I don't have many slides here actually.
So millimeter wave communications.
Yes.
There's a lot of attention devoted to beam sweeping.
Correct.
Because you want to illuminate a narrow beam, path
Correct.
loss is an issue.
Correct.
Given that this is also operating at 70 gigahertz, you would still have a range problem. Unless you're limiting by 100, 200 meters, you won't be able to go further than that.
Correct.
So is there also beam sweeping done in radars in practice?
Yes. So all of these automotive radars, right, they operate even both in beamforming mode, which is what beamforming means, TX beamforming. You put a phase shifter and then focus in one direction. And also in MIMO mode, where you get a whole sweep in one shot. So radars, automotive radars, for example, right, the distances we are looking at is maybe like 250, 300 meters, 350. That's the maximum we are looking at. And at 77 gigahertz, we are able to reach that distance with sufficient number of antennas.
And another question is, the other issue that arises in millimeter wave cellular is you've kind of got to choose the transmit receive beam pair together. Like, is there a similar issue here, or?
What do you mean by that actually?
So, for example, your transmitter could point in one direction, the beam. The receiver would also need to
Correct.
do that. But is that issue coming here?
Yes. So, for example, if you have a transmitter, you have a sequence of transmitters, you want to focus in a particular direction. Those transmitters, you would put their phase shifts in the correct way to focus in that direction. Once you focus there, right, all that cumulative sum of all those transmit antennas will hit that target and come back. It will be received by all the receive antennas. Now, the receive antennas also need to beamform digitally, right? They will all receive the signal, but then they have to combine them with the appropriate phase shifts to see the target in that direction. So the receive side beamforming actually is done digitally, but the transmit one has to be done by applying phase shifts to the transmitters.
Like for automotive radars, why are we seeing such a large range? Like, why do we need such a large range for automotive radars?
It is basically, so for example, think of highway driving in an autobahn, people are at 200 kilometers per hour, and there's a car in front that is stopped, right? It's a question of, you detect a target, then you need enough reaction time and so on, right? So I think, I don't know, if you say 200 kilometers per hour, 300 meters, I don't know, maybe it's like 5-6 seconds or something. I'm not sure.
I'm thinking of Bangalore traffic, so
Bangalore traffic, I think, right, I told you that we have radars are not good in, we have limited spatial resolution, right? So Bangalore traffic, there's going to be cars everywhere, that the spatial resolution will suffer. But this is more for highway driving, right? Okay. So 3 topics that I wanted to kind of focus on here, right? So this is more, I think, just give you a sense of what are the challenges in these areas, what are the kind of the things that people are doing, right? But these are all, I would say, open areas for research of relevance to the industry. So first thing we've already talked about, right? Angular resolution is limited in radar. So how do you enhance angular resolution? So let's go at that. So I mean, basically, right, if you have a sequence of antennas, if you do an FFT after the range and Doppler processing, right, so has been done, you get you do an FFT, you get a peak here. Now, if there are actually two targets here, right, the way to resolve them is to have more antennas. The moment you have more antennas, you can see that this peak actually is two targets. So a larger antenna aperture is better resolution, right? So one way to improve angular resolution is with cascading. So cascading basically is you take multiple devices. So you have this antenna array which has a large aperture, a lot of antennas. Few of the antennas are associated with one or routed to one device. The other antennas are routed to the other device. You need synchronization signals. So the synthesizer has to be generated from one device. The synchronization of the ADC and all of that has to happen between both of these. And so that's one way that you can get this larger, antenna array and increase the angular resolution, right? The other way is to go to more signal processing and algorithms. So come up with a sparse array configuration, which is basically the same aperture. So the aperture defines the resolution. So you have the same aperture, but you have fewer antennas because each device can only service a limited number of antennas. You then have careful array design coupled with specialized algorithms, and this is basically a way of trading off hardware cost for algorithmic complexity. So these algorithms are going to be significantly more complex. So this is the sea of various algorithms that are being used or that are being looked at in this context. Like if you have sparse arrays, or even if you have non-sparse arrays, right? How do you get better resolution than just with an FFT? So this is all the sea of acronyms and different algorithms here. So I won't go into too much detail on this, but some of you might have realized that there are some things here like I don't know, OMP, BPDN, and all of that, which are for people who are familiar with compressive sensing or sparse algorithms, right? These kind of algorithms are used. So in this angle resolution rate, one thing that is often assumed is that the signals are sparse. So the question is, why are we making that assumptions that the input to the angle processing, the input is sparse? What is the basis for that assumption? Any guesses?
In an environment, there will be only few cars that will be there. If you take a 3D cube kind of processing, there will be only few points within that complete 3D sampled 3D cube that will be occupied. So that's why.
Okay, I think maybe you're getting at the same thing. So the thing is that radar, right, separates things in range, velocity, and angle. So once you do a range processing, any target which has a different range from other targets gets separated out. So they are not going to be interfering in your processing. Again, once you do velocity processing, targets which have different velocities get separated out. So the only things that have to be resolved in the angle part, right, is the targets which have the same range, the same relative velocity, and happen to have different angles of arrival, right? So that is the reason why you make that assumption of sparsity, or you can make that. So so I think we talked about cascading, which is like a brute force hardware method. This is signal processing method. In the signal processing itself, right? So these are all traditional signal processing algorithms. There are also angular resolution with machine learning. So this is some thing that people have started looking at in the past few years. So why would you use machine learning for angular resolution? So one thing, some of the advantages could be, right? Antenna non-idealities can be difficult to model. So you can have antenna non-idealities where you have coupling between them. The coupling also can be dependent on the angle of arrival itself, and so on. So it's not easy to get a model for some of these antennas on a board. So you can get it, the model, if you have a lot of data, hopefully the model will learn it. You can leverage statistics of the data. So typically, antennas have the beam is strongest in the center and then dies down. So some of the statistics could be, typically if the angle of arrival is close to 0 degrees, right, the targets are stronger. Targets away from them are weaker. There could be other such statistics, and I'm just giving an example of the top of my head, but various statistics that we are not recognizing that may be there in the data. The other thing is efficient compute. So if you look at machine learning, right, there are many efficient compute because it's all multiply, add, and then followed by nonlinear operation, right? So if you can frame your problem in that context, right, there is already existing efficient hardware which can run that. So that is the reasons why you might want to look at machine learning. And okay, we can get this later. Okay, so if you look at angle of arrival, right, typically what you do is you have these antennas, you get signals from the antennas, after doing your range and velocity processing. You do something, simple thing could be an FFT here, right? It could be FFT, it could be music or some other, fancier algorithms, but you do something which gives you a spectrum. Then you do peak detection. So this is how typically angle estimation works. You have an algorithm which generates a spectrum, and then you do peak detection on that, which will give you the estimates of the angles of the various targets that you're seeing. So there are approaches in literature where you replace this by a deep learning network. There are some other, so the output of that network will be to generate a spectrum actually. There are some other approaches which look at this whole thing and try to replace it by a deep learning network, and then the output of that will be angle estimates. So this is a particular, if you're looking at kind of seeing what is the current state of art or state of research in this particular field, right? There is this particular paper which is quite nice. It has a survey of all the different techniques that different people have tried, and a lot of references that are there associated with this paper. So you can look at that.
You mentioned velocity, but
yes.
You're able to pick up only the relative speed in the direction to the
Correct.
antenna. Right?
Correct.
Just
That is a limitation. So it's only relative velocity. So tangential velocity will not be observed. Tangential velocity has to be inferred to a tracker or something across time. So this is a middle ground. So I think the thing that I talked about here, right, this is purely deep learning, right? Just throw away the regular algorithms that are there and just replace it by a deep learning network. There is something else here. I'm calling it signal processing inspired machine learning. So the motivation for this is, or the way this works is that you take an iterative signal processing technique. Some of the model parameters in it, you make it learnable, unroll it a few times. So that seems to be the general concept here. I think it's in the literature, it's called algorithm unrolling. Advantages could be, better generalizability because the network itself, the structure is based on something that already exists. Maybe better interpretability. People always ask, how does this work? Why does this work? So here, there's a chance of better interpretability. One example of this, right, like a leading example of this is basically, there is a sparse, popular sparse array problem, right? You have something like AX equal to B, where A is M cross N, X is N cross 1, B is M cross 1, and your B is the observable, A is given. You have to estimate a sparse version of X. Right, and there is a solution called iterative soft thresholding algorithm, which is algorithm that people typically use to solve, or one of the ways in which people solve this problem. So if you look at that particular algorithm, right, this stuff here, actually this is an iterative algorithm. Xk plus 1 is the k plus 1th estimate of X. And then you have some stuff going on here, which is actually a linear operation on this Xk, followed by this non-linear operation, which is called a soft thresholding operator. So if you look at this, right, it's a linear operation followed by a non-linear operation repeated a few times, and this can be taken as a baseline to make this A, for example, learnable, unroll this a few times, and that kind of a thing. So I won't go into the details of this, but okay, I was planning to go, but I'll skip that. But if you're interested in knowing more about that, right, this is the paper which kind of very popular paper, a lot of citations. Which is kind of foundational work, I would say, in unrolling iterative algorithms into deep learning networks. So one of the authors is Lakoon here, who is one of the famous guys in machine learning, right? And there's another review paper on how this has generated other research in this field, and it's called algorithm unrolling, that concept. This is a survey paper that you can also look at if you're interested in knowing more about this particular field. Yeah.
So I was wondering, so essentially you're looking at replacing the angular FFT part of it, the signal
Yes.
processing,
Yes.
with an ML-based approach.
Yes.
Will it result in improved angular resolution, or are we just looking at the replacement of one angular resolution computation with another?
No, so it has to be better in some way. So it either has to be better in the compute. It could be compute is lesser, or the compute is the same, but I'm now putting it in the framework of linear operation followed by nonlinear, which makes it because there's very efficient compute structures that are available for that. So that could be one. The other thing could be better resolution, right? So the goal is better resolution, but you can frame it anyway. You can also frame it as lesser compute for the same resolution. It could also mean that you are, if you have difficulties getting the model of these non-idealities in your system, antenna. So because antenna is such a weak link in radar, right, the non-idealities matter more. In range and velocity, you have so many chirps and so many ADC samples that a little bit of non-linearity is not an issue. But in antenna, you have so few antennas, you want to get the best out of them, right? The modeling of those non-idealities has to be really good. So maybe machine learning can help you do that. So the goal here is to go to machine learning is to have better performance.
What about power? You said implementation. I mean,
Yes.
you said computational complexity.
Yes.
But an FFT FFTs have been optimized to be very power efficient over the edges.
Correct.
Over the years.
Correct.
Now, if you now replace that with an AI/ML based system.
So the thing is that this AI/ML is not competing with an FFT. This AI/ML is competing with some of those sparse array algorithms and music and other things which are already compute intensive to begin with.
Okay, got it.
Yeah.
Thank you.
So, so I think if you're looking at angle estimation, right, it's a problem in radar because we have we want to do with as few antennas as possible, but an ideal angle estimation algorithm, right, should meet whatever specs that you have, acceptable computational complexity, support high dynamic range and target strength. So you could have one target which is a truck and another target which is a like bicycle. Motorbike or something, right? So both of these targets should be seen or resolved, robust to antenna non-idealities. And then, okay, the other thing here is same antenna arrays must be able to trade off angle resolution with computational complexity. So sometimes what happens is you make an antenna array which is so sparse that the only way you can get anything meaningful out of it is by applying a really complex algorithm on it. But in radar, right, you have a scene which has so many points. You want to say for certain points, right, as long as my car is not driving in that direction, I don't care if the angle resolution is very high or not. So I want to be able to use that same array and say if I do an FFT, I should get meaningful results on it. But if I want to do something better than an FFT, I can expend more compute and get better results. So that same antenna should also be amenable to, for example, a simple FFT. And if an antenna structure is very sparse, that may not be possible, right? So that is something to keep in mind. Single snapshot, so in automotive radar especially, right, in other, maybe not other applications, not so much. Single snapshot means you take one snapshot and you want to get the result. You don't have the time to take multiple snapshots. Okay, so the next one is need for classification, right? So typically people are talking about radar. Okay, traditionally radar is basically a target, tracking, estimating the target's location and velocity and then track the target, right? But radar is evolving from purely detection and tracking problems to also include target classification. So for example, in automotive case, it may be classifying road users, as any of these kinds to figure out which is more vulnerable and not. In the non-automotive space, there are a lot more interesting applications. So intruder detection, right? We talked about radar being very sensitive to motion. So if you have an intruder detection system, right, if there is motion, it will easily detect it, right? That's not a problem. Now the question is this motion because of a real intruder, or is it just because a tree is moving or a curtain is shaking or a fan is rotating or the vacuum robo or something like that, right? So classifying the sources of motion is one example where you need classification. Elderly care, fall detection. So if you have a radar in a room and it can detect falls. Gesture recognition. So all of these, if you look at it, right, at least the last three here, it's basically, right, radar we said is good in motion, or it has good velocity resolution, right? So all of these are kind of talking about identifying motion signatures because the spatial component of these radars is not going to be that great, especially in these kind of applications, right? The number of antennas is very limited because the cost is, it's more sensitive to cost than automotive radars. So here, it's all about identifying those motion signatures from your velocity resolution, right? Now, vision or camera, right, is very in an advanced stage. A lot of research has been done for several decades, right, in terms of machine learning and camera or vision. Not so with radar, but of course, all the progress that people have made in cameras, we can take that stuff and apply it to radar and see how it works, right? But some differences are there, right? For example, Vision has better spatial resolution but limited or no angular range resolution. Radar is the other way around. So the nature of the signals are going to be different, but architectures that people have come up with vision continue to be the what people look up to when trying out things in this space. So just to give you an intuitive sense of motion signature, so if you have this, we talked about range and velocity plot, right? If you have a single antenna, you can send multiple chirps and get this kind of range velocity plot. So if you have a car moving towards a radar, so this is a radar, if the bulk of the car is moving with the same velocity, if you ignore the wheels, right? And so you would see probably a single block here, it's a one single velocity. But if you have a person moving, right, you have his legs moving in front, the hands are moving back. So if you have a good enough velocity resolution, right, you may be able to see those finer details of this human motion. So that's what we mean by motion signatures, and a lot of this ML classification is kind of primarily tries to leverage this kind of motion signature to classify things, classify targets. So this is just different ways in which you can see things approached in literature. So you do some basic FFT processing. You can get, so this for simplicity I'm showing here, it's a single antenna, so you are only resolving in range and velocity. You get some kind of a range velocity plot here. You can send this to this is like an image, so you can send it to a time distributed CNN. So whenever you want to do classification in radar, right, one thing is that you have to get signatures for a particular frame. So this is an image for one frame. But for motion signatures, you really have to look at multiple frames. So you also have to look at how this frame, this image is evolving across time. So which is why I mentioned a time distributed CNN followed by an RNN, for example. Other thing is handcrafted features. So handcrafted features is we know what kind of application we are looking at. So we humans, engineers have some intuition. We try to get out some statistics from this image and then pass it through a simpler network. So the contrast between these two is here lesser dependence on domain knowledge, could be increased computational complexity and need for a larger data set. The reason is that here the human handcrafted feature extraction, right, has taken out some of the, some intuition is already embedded in here. So you don't need a larger data set. So for example, here, right, if you don't have a large enough data set, there could be things like, if you're taking a, if you are, trying to, let's say, separate between a tree and a person, and when you took the data, the tree always happened to be the left and the person is to the right. So this network can learn that, okay, if something is to the left, I have to say it's a tree, and if it's to the right, it can learn wrong cues unless your data is really large and has a lot of things, has sufficient data to cover all those cases, right? But with handcrafted feature extraction, some of that is already, maybe extracted out by a human intuition. Okay, so there are also some, here we talked about, operating at this range, at the level of these heat maps, we call these things as heat maps. But there are also places where, people do detection and tracking. So detection means you basically look at these heat maps, you find where are your targets, strong targets, you do clustering and tracking. And you can look at this output of this tracker, maybe also, look at that tracker, go back to this heat map and pick up the relevant portions and so on and do some, classification. So this may be useful if there are multiple targets in the scene and you want to classify each of them. Okay, I think I'm going to skip these things here. Okay, but if you want to get a good introductory, if you're looking for introductory resources for ML, for millimeter wave radar, right, there's one Signal Processing magazine article from a few years ago, which is quite comprehensive. TI also has a white paper specifically talking about what some of the stuff that can be done with this particular device, which is a device which operates in the 60 gig band. Okay, so the last one here is problem of interference mitigation. So basically, as the number of radars, as the number of cars with radars increases, and the number of radars per car also increases, right? Radar interference is a big problem, and the main thing here is that, right, interfering signal can be significantly higher than the target signal. So here you have a car, it has a radar, it sent a signal here, it is to hit this, the signal has hit this car and it's come back. So by the time the signal goes there and comes back, it's very weak. But that's the car this car wants to detect, that's the obstacle in front. There's another car driving by and, this car is very near. So the signal from here is going to be very strong. So this is an important problem, and, there are people in academia looking at it. There are also people in industry looking at it. And there are also some consortiums that have been formed at different points in time where, industry and governments and all that come together and try to do some research on this. So these are all mainly European consortia. So basically, right, just to give an intuitive sense for this interference, we talked about this chirp, right? This is a range versus frequency versus time. So this is the chirp that you're sending. There's another interfering chirp here. Right now, it turns out that because of the way FMCW radar works, right, you have this down conversion, you transmit something, you receive something, you down convert it, you have an aliasing filter and all that stuff, right? For anything to be interfering, it has to be in this gray zone here. So I won't go into the details, but even if there's a signal that is, this red signal is an interfering signal, but in this portion, right, it's not in the gray zone. So even though it's overlapping in time, it is not going to be seen in the IF spectrum of this particular targets, this particular radar's IF spectrum. Only things in this gray zone, and this gray zone is defined by how far do you want this radar to see. So this is the zone where things will be interfering. And if you look at this in this example, right, you have a particular IF signal for this particular radar. I sent out something, it's got a received signal, and this is a signal corresponding to the target, right, a sine wave corresponding to target. This portion has got corrupted. Now, if I didn't do anything and took an FFT on this, right, I might get something like this red FFT. So I'm seeing a target, some strong target here, but this weaker target has got buried. But if I were not interference limit, if there was no interference, right, if only this blue signal was there, I would have been able to see both targets. So basically this interferer here has kind of created after the FFT, right, this noise, you can consider this as noise. This has got spread out and it has increased the noise floor, basically occluding weaker targets. So that's kind of that's how interference, hampers radar's performance. So some simple techniques that people have been using, is, identify these regions of. So the first thing you have to do is, right, you have to detect interference, and typically, right, or the most destructive interference is typically much higher in signal. So you can use some statistics that rely on signal strength and identify the regions that are corrupted by interference. You can do a simple zeroing out. You can do a linear interpolation. There are also more complex iterative schemes and so on. But one thing is that these state of art or whatever is available in radar devices, right, with respect to interference mitigation, it's far from perfect, but it's been improving from generation to generation. But it's still very much an open problem. But so, if you want to look at this problem, how do you pose this problem as a mathematical problem, right? So you have a 3D set of ADC samples that you've collected across chirps, across samples, across chirps, across antennas. You need to identify samples that are corrupted by interference and reconstruct the corrupted samples. That's basically the problem. And the quality of the reconstructed signal should be sufficient to not occlude weaker targets. So how good your interference scheme is, for one thing, it would depend on how much of complexity it has. Second thing is, how much is the maximum range reduced because of this. So for example, without interference, I can see up to 250 meters, but with interference, I can only see up to 100 meters. But if there's some other interference scheme that can let you see up to 150 meters, right, that's better. So this is the kind of problem of interference. So far we talked about reactive. Reactive schemes means interference has happened and now we are trying to kind of fix it. Right, there are also various proactive schemes, so sense and avoid. So you sense that there's a spectrum, that there's interference, and you switch to a different band. I mean, that has to be within the band that you're given from a regulation point of view. Dithering, so dithering some of the transmit and receive parameters or transmit parameters to hope that interference doesn't keep happening exactly at the same time. There's also things that people are talking about in terms of coordinating radar transmission across automobiles so that they occupy non-overlapping time and frequency zones. So the first two things are happening right now. Some form of this is happening right now. I mean, this is something that people are talking about, but it's not really something that is standardized or anywhere close to standardization. But definitely there are people talking about this as well. Yeah, so I think that is all I had. So I think we talked about three problems, right? Three potential areas of research. So angle resolution improvement, classification, and interference mitigation. I think just one thing I want to add is I think finding an ideal radar modulation scheme is also something that people are looking at. So an ideal radar, right, it should be, what is an ideal radar modulation scheme? So one thing is it has to have good resolution, range resolution, velocity resolution, and so on. Should enable simpler analog and RF should be less susceptible to interference. So if there's something natively in the modulation scheme that makes it less susceptible to interference, that is good. The other thing, other thing is, to improve angular resolution, then it requires you to multiplex different transmitters. So a modulation scheme that makes it easier to multiplex different transmitters without having a particularly bad side effect. So like time division multiplexing in FMCW radars reduces the Vmax because you are putting different transmitters in sequence. But if there's some other way to get around that in a different modulation scheme, that's an advantage. Lastly, and this is not that important right now in the industry, but if you can do communication and radar at the same time, that's also great. But yeah, I think that's pretty much I think I'll end my talk here. But, yeah. So, open to questions. Yeah.
On MIMO radar, see, if you're looking at 60 gigahertz, you're looking at 5 lambda.
Correct.
So space is really not an issue. It just seems the main issue is the RF chain required for each antenna. Is that the bottleneck?
Lambda by 2, right? Spacing will be lambda by 2 between the two of them. So spacing can also be an issue depending on the things. So if you want to put these radars in a thermostat, in consumer applications or in your phone or AC, things like that, right? It is an issue. But apart from that, yes, it is the RF, the hardware cost.
It's just that you have to have multiple RF chips.
Correct.
So then there are these often series of techniques like this, what are called hybrid techniques or selection techniques, where you switch on antennas sequentially, like you mentioned, or use few RF chains but turn on all antennas.
So there is one way by which, for example, there's called antenna switching. So basically, you have one or maybe fewer RF receive chains, but you keep switching. The first antenna goes to that chain, and the second antenna goes to that chain. So that is something that people are doing. I have not seen it done in automotive radar, because automotive radar, right, the switching typically, so one thing is switching takes time. So if you want to measure high velocity, right, by the time you switch one whole cycle and come back, you would have lost the velocity that you want to measure. Second thing is the switching typically also has a loss in terms of dB because of the switcher. So in automotive radar, I have not seen that, but in consumer applications where high velocity is not an important thing, yes, antenna switching, having the antennas, but switching the antennas with a single receive chain is possible.
Second question, but totally different. Again, MIMO radar. I had asked you this question about full duplex, and you said you could. So it seems like you would have to put your high pass filter before the LNA. Otherwise, you will be saturating out your LNA.
No, yes, but we don't have. So the way it works, at least in the way FMCW radar right now works, the LNA will see that flooding. LNA will see that flooding, and ADC will not see it. Yes, that is how it has to be designed. Yes. I don't know if you had any suggestions on that front.
No, I think you're right. We have to avoid keeping that filter right at the front. Because it just affects the overall signal chain noise figure. Okay. And then really messes things up. So I had a question for you on interference mitigation, which I don't see mentioned much, but I was wondering what your thoughts are. Which is, the military radars for a long time used phase coding, right? Barker codes and all these things. And as you know, if you do these things in code domain, like CDMA tends to help with interference, you can actually mitigate interference. PMCW is probably the latest spin on that. So I wanted to understand your opinion on, just get your opinion on.
So one thing, right, I think PMCW was a strong contender. I think right now somehow it is not getting a lot of traction in the industry. But I think from a technical point of view, right, and we've also looked at it a lot. So I can tell you my opinion. So one thing that is acknowledged in PMCW, right, in FMCW radar, targets that are the coupling signature can be removed with a high pass filter. In PMCW, that's not the case, because even the coupling will be coded. It will no longer be like small low frequency that you can remove, right? So for that, what they do is they try to do some active cancellation scheme, trying to figure out where the bumper is or where the reflector is, and typically those things don't work that well. That is one thing. The other thing that people talk about, right, it's that the perception is that PMCW is better in interference, right? That actually is not true. So one thing, right, if you look at it, right, if you look at FMCW radar as well, this interference is localized. Once I do an FFT, the interference is spread, which is the same thing as what PMCW radar would do. So there is some natural spreading occurring here. The second thing, right, in FMCW radar, not in all cases, but in cases such as the one that I show here, interference is localized. So the moment interference is localized, there is a possibility of identifying that segment, removing it and reconstructing it. If your interference is everywhere, right, then that option is not there. So I would say that, there is natural spreading occurring in FMCW as well, because the FFTs will spread things out. If there's anything localized at the input in FFT, it will localize, spread it out. And PMCW has this problem of near range coupling is more difficult to remove, right? Yeah, so every modulation scheme has some pluses and minuses, so I think definitely PMCW is also something worth considering. But some of the sound bites that people say interference mitigation in PMCW because CDMA, right, that is not true. At least that's what we feel. We have done some analysis on that.
Yeah. Yes, right. One or two. Yeah, thank you. Good presentation. So I have one quick question. So do we have the problem of ghost targets in the systems you are talking about with the FFCW?
Ghost targets means multipath related?
Multi-targets, multiple targets. The question is, suppose you use a single ramp, right?
Yes.
But is there a reason for you to use in the current systems an up chip and a down chip together in one single link? It is not used?
We don't use that. So that up chirp and down chirp, right, usually what happens is that is an older system where people used to be, so you would have a chirp like this and a chirp like this.
Right.
And you would look at your targets here and your targets here, and you would have to have so here what happens, right? So right now this is I think this is what you're talking about. Right now this is replaced by this. So this was the old system where, people could not build chirps which were ramping very fast. So you would have a slow ramping chirp and a slow ramp down chirp. So now what happens is that you don't have a 2D, at the output of this, right, you'll have a 2D grid which will then tell you the range and velocity of all targets. Here what happens is you'd have this thing, you can do a range FFT of this target, of this chirp. You have this down chirp, you can also do a range FFT of that. Then you have to correlate these peaks, like this target A could maybe be here and the corresponding peak is here. This is target B. Then you need to compare these two and then estimate the velocity using some equations. It's pretty simple, but the thing is that in a cluttered scene where you have many targets, right, this association problem might become difficult. And nowadays, right, with devices being able to ramp chirps very fast, you can pack multiple chirps in that same duration. And you can, at the output of this, if you do a 2D FFT, you get a grid which has the range and velocity of all the targets. So it is, it's more complex, the method I mentioned, but I think because of FFT accelerators and the state of art nowadays, it is not a problem. It's not considered a problem. Yeah.
Okay, so I think it's an implementation issue which fixes that, what do you call it, multiple target scenario, but then ghosts will be created because I think what we did not talk about or did not hear about is the ambiguity function of the waveform. And the ambiguity function of this waveform, which is FMCW is a line. If you have multiple targets, you will have multiple lines. And if you have an up chirp and a down chirp, you have multiple intersection points which are not valid one. Yes, you will have ambiguous targets which are ghosts.
Correct.
So you seem to suggest that you don't use up and down chirps.
Correct.
So I don't know whether in your new frame of things where you have only upslope always for a certain number of iterations, certain number of
we don't have downslopes at all.
You don't have ghosts.
At all. No.
You don't have ghosts,
No.
so that is okay. The last question is, you showed a heat map.
Yes.
What is that scene?
Okay, that particular scene, that heat map that I showed was actually a gesture scene. So it was a hand moving in front of the radar, which is why you see, I think maybe this one or this one, right? Yeah, so this is actually, this particular one heat map is from a gesture scene. So it's something really near range, and that's why you can see, different parts of the hand or other things there. So it's a very, that's why it looks very crowded. Yeah, it's just the, maybe, if I have radar here and if I'm moving my hand like this, it's just that portion here. It's a very, the range could be maybe like 1 meter or half a meter or something. So which is why you see a lot of stuff going on there. In a typical automotive radar scene, in a highway, you would see more sparse targets. Yeah. Go ahead.
Are we replacing radar with some current technology equipment which is doing the work of radar, or we are adding on radar to the current automotive technology for range detection?
So this is radar is being added on, right? Radar is being added on. So right now radar is used, commonly used in automatic cruise control, right? So radar camera, right, has some, you know, things which radar can complement, right? Accurate range measurement, velocity measurement. So if you're driving on a highway and there's a car in front of you and you want to maintain a fixed distance from that car, right, radar is used. If you're doing a lane change, you know, the moment you put on your indicator, in some of the cars, you know, in US and Europe, you can see on your rear view mirror, on the side rear view mirror, a light will start shining if there's a car next to you. So that is done using radar. So those are driver assistance features that are on top of camera right now. Yeah.
Sorry, can we take more questions in the back? It's already 5:20. Thanks. So.
No problem, no problem.
Thank you so much for accepting our request and giving such an engaging talk. Thank you everyone for attending, and we have arranged for refreshments at the coffee hut. If you want to connect further, please, you can connect over coffee. Thank you.
Thank you. Thanks.